Welcome everyone to another session of the String Pheno seminars. Today we will start with Margherita Putti, who is going to tell us about the heterotic axiverse. So please take it away.
Okay, so well, first, thanks a lot for having me. I'm gonna tell you about this work that I did recently with my collaborators, Jacob Lido and Alexander Westphal. Yeah, on exploring the heterotic axiverse. So let's kind of jump in if I can. Okay. So just a little bit of an introduction on axions and whatever. So we know axions, they've been introduced to solve the strong CP problem, but they're really interesting for us because they're ubiquitous in string compactifications. They have a lot of phenomenological roles, so they are very well explored from the bottom up. So they can be, again, QCD, they can be dark matter, they can play roles in inflation, there can be dark radiation and also other things. And again, the reason why we like them very much is because of the axiverse, so the idea that there are many, many axions that have hierarchical masses and couplings. So we know that in QFT, they arise as massless modes after spontaneous symmetry breaking. In string theory, usually we think of them as coming from p-form gauge potential. So we know we have the p-forms. And whenever we compactify, we go from the 10-dimensional space-time to 4D times the extra dimensions. And this process of compactification gives rise to the axions. So our p-forms, we expand them in harmonic forms, and then we have the coefficients, these AIs, which will be the zero forms, which are our axions. So basically, once we integrate over a p-cycle, a p-form, we have a zero mode, which is our axion, a zero form, which is our axion. We know that there can be as many axions as there are non-trivial p-cycles. So this is given by H11, so this number here. And this tells us how many axions we have in our compactification, and it can be from some order few to order 100. So that's why the idea of the axiverse, the idea of a universe filled with axions. So they get the masses from non-perturbative corrections. So these instant online contributions, so ED1s, ED3s, gauging condensation. They're very nice because they have a very high quality. So their shift symmetry arises is inherited by the higher dimensional gauge symmetry or the p-form gauge symmetry. Um, and they can be used to build inflationary models, quintessence models, again, dark matter, etc., etc. And so that's why they're known to be, I mean, the axiverse is known to be one of the best prospects to tie string theory to experiments. So usually when we talk about the axiverse, we talk about it in type 2b. So we know there we have p forms, we have the C0, the B2, the C2, and the C4, and they are the candidates for our p form axions. And we know that in type 2b, our gauge fields will come from the D branes. So for example, if we have a D7 brane, we wrap a fourth cycle, and automatically this gives us a gauge theory that is coupled to an axion. So a D7 brane, right, is an 8-dimensional object. So once you wrap it on a fourth cycle, the extra, like the three, four legs, let's say, will give us the four-dimensional F. And then in the internal, let's say, dimensions, we have the C4 axion, so the integral over a fourth cycle of C4, which is exactly what we were looking at before. So this gives us automatically a Chern-Simons coupling between the C4 axion and the gauge field. However, this means that in type 2b, axions don't have to couple to the standard model necessarily. For example, if we have the standard model on some specific cycles, we can have that it doesn't have to be the same cycle where other axions are. So it will not be, right? Generically, the case will be where we have many axions and only some of them will be coupled to the standard model. Most of them, we imagine that they will not be directly coupled. They might be indirectly coupled via kinetic mixing, etc., but they're not directly. So the point is that we have a lot of different scales. We have a broad range of axion masses and decay constants. And we have that axions can couple or not couple to the standard model. So the type 2b axiverse is very flexible, which is good, but at the same time is not highly constrained. Somehow we can manage to arrange things in a way in which we can try to have couplings the kind of the way we like it, right? And so the idea was to try to look at what happens in the heterotic axiverse, if this is the same thing. Because the point is that in the heterotic string theory, you don't need d-branes to have the gauge theories. You already have them at the background. So either you have E8 cross E8 or SO32. So all fields will come from the closed string sector. So this is the action, the ten-dimensional action. So we have gravity, we have the kinetic terms, the fermions, and then we have the Green-Schwarz term, which will give us our axion gauge coupling. So we have a single fundamental scale that comes from the 10 dimensions, and we have that gauge and gravity are already unified at tree level. So again, yes, the axion gauge coupling comes from this extra Green-Schwarz term. And the point is that this means that we will have a very strong constraint. In general, heterotic string theory is very predictive. So the question is, what is the dark axiverse in heterotic string theory? How does it couple to the gauge sector? Is it as free somehow as in type 2b, or is it restrictive as well? Um, and so this was kind of a bit the introduction. Let me give you a bit of a roadmap. So we'll go through the heterotic axions, so the origin, where they come from, um, the source of the potential, so their masses. We'll see what solving the strong CP problem means in the heterotic axiverse. And then we'll try to give I'll try to give some explicit examples if I have time. Otherwise, we kind of will skip through it. Uh, but if you are not interested or you want to decouple, and I don't know, this is the type of things we will see. So this is a specific example. So we have, I don't know, gaugino condensation. Is it present? Are we in an isotropic compactification? What are the masses of our axions? Can we solve the strong CP problem? Can there be a fuzzy dark matter axion? So this is kind of the idea, the questions that we want to address and that we will address, and we'll see what they actually mean. Okay. Again, a little bit about the heterotic strings. So we said that it has gauge theory already at the background level. So there is no need for d-branes to get a gauge group. So we have either E8 cross E8 or SO32. But the standard model, right, is not E8 cross E8 or SO32. So what you do is that you compactify an Calabi-Yau that has a non-trivial gauge bundle. And what this does is that it breaks one of the gauge sectors. So in this talk, we'll just look at E8 cross E8, not SO32, but the story is similar. So what you do is that you break one of the gauge sectors to G cross H, and the commutant H will give us the 4D gauge content. So typically what people do is that you take in the first T8 some gauge bundles such that in 4 dimension you have a godlike theory, and then your second D8 is a dark sector. So you can stay E8 or you can break it as well. You can kind of decide. Okay, so from the 10-dimensional action, we can dimension reduce it, and we find our 4-dimensional action. The three terms which are important to us are these three terms here. So we have the R term, the F wedge star F, and then H wedge star H. And the real point is that all of the, let's say, coefficients that we have, all of the scales that we have, all of the couplings, they are not separate, but they all come from the 10-dimensional action. So there is no real parametric separation between these. So if we look, for example, so we know that V is the volume of the Calabi-Yau. So for example, the Planck mass is just the volume, the overall volume of the Calabi-Yau over the string coupling square. The Young-Mills coupling, so alpha Young-Mills, is just given by G string square over the volume of the Calabi-Yau. The string mass is related to alpha Young-Mills and the Planck mass. So the point is, once I set the Young-Mills coupling, and I set it to be the gut-like, if I want a gut-like theory, right, I set it to be alpha gut, which is 1 over 25, then this gives me already the string scale, so the string mass, which is the Planck mass over 18. And the point is that if I plug this here again, I get that the overall volume of my Calabi-Yau is actually equal to the string coupling squared times 25, which was the 1 over 25 here, which tells me that I have an upper bound on the overall volume of the Calabi-Yau because I want to stay in perturbative heterotic string theory, and therefore this must be smaller than 25. So the point is that this is what I was trying to say when I was saying that heterotic string theory is very constrained in the sense that you have a lot of predictivity because you know what the scales are, you know what the couplings are, but they come at the price of reduced parametric freedom. So this is going to be kind of the main focus, let's say the main starting point out of all the things that I'm going to say next. So now we look at our axions. So they all come from the 10-dimensional B2 field. So we have two types of axions. We have either the universal axion, which is just the integral over the overall Calabi-Yau of the dual of the B2, so the B6. And this is universal in the sense that it just counts for every Calabi-Yau. That's why it's called universal axion or model independent axion. But yeah, so model independent is kind of weird. And then the BIs, instead, they are the model dependent axions. And they're the usual, let's say, P-form axions. So they're the integrals over two cycles of the B2. So the B2 expanded in harmonic forms. Now BIs will be the axions and BIs are the harmonic forms. So once we plug in the Bianchi identity, we impose it basically via Lagrange multiplier. And then what happens is, well, we can integrate out H and we get an action for the model D independent axion, so the universal axion, S of A. And this tells us both the axion decay constant and the coupling that it has to the gauge fields, so trace F wedge F, and also to the curvature trace R wedge R. So the decay constant is just given by the string coupling to the fourth over the overall volume of the Calabi-Yau. So we can read off also from the kinetic term the decay constant of the model dependent axions will be. So where this gamma ij is just basically the Kähler metric, and so the decay constant will be proportional to some volumes of two cycles over the string coupling squared. Then to find what the coupling between the model dependent axions and the gauge field is, we have to look at the Green-Schwarz term, which is this B wedge x8, where x8 is this whole thing here is the anomaly polynomial. And so what happens is that, again, once you dimension reduce everything, you find that your Chern-Simons Lagrangian is something that looks like this. So you have Ni over 16 pi squared, Bi, times the trace 1 f wedge f minus trace 2 f wedge f. So here for trace 1 and trace 2, I mean the trace of the first D8 or the trace of the second D8. So what happens is that the BIs are coupled to the first D8 and the second D8 in the same way via this Ni, where this Ni is given to you by the integral over the Calabi-Yau of the harmonic form wedge this trace 1 f wedge f, where f now is the f bar, so the internal one. So the one coming from the gauge bundle, and the internal curvature. So we can rewrite this as the BI wedge, the second Chern class of the gauge bundle minus the second Chern class of the tangent bundle. So everything is kind of known, is set. And so again here, I can, just to make it clear again, the point is that the axions look like they're coupled equally to the visible and the hidden sector. So we know A couples to trace 1 f wedge f, but A also couples to trace 2 f wedge f, similar in the exact same way. And also for the BIs, we have the same thing, but with a minus sign, right? So what happens is that the thing that couples to the first D8 is A plus the sum over I and IBI, and the things that couple to the second D8 is A minus the sum over I and IBI. So it looks like we cannot do much because everything is coupled in exactly the same way. But actually, it's not really the end of the story because you need to canonically normalize both the axion and the gauge field. So once you do that, what happens is that you want to have something which is something that looks like lambda, so some number times theta over f times the trace of f wedge f, where now f is the canonically normalized one, so with the gauge coupling that is kind of transferred here. And so the thing that you will see is that the model independent axion, so the universal axion, is just theta a over fa trace 1 f wedge f, and also for the second trace is the same, whereas the different lambdas are actually not really the same. the lambdas will be the ni, so the ni that this ni here, over the real part of the gauge kinetic function, where the gauge kinetic function is given to you by the overall volume of the Calabi-Yau over the string coupling squared plus IA plus or minus, depending on the first or second d8, the sum over I of Ti and I, where Ti are just the Kerr fields. So you have the Vi, which are these two cycle volumes, plus IBI, which are the axions. So just to finish up with all these I's, the point is that the couplings of the model-dependent axion to the first D8 and to the second D8 are very similar, but they have a relative minus sign in the denominator, which means that I can enhance one or the other without, like I can enhance one with and decrease the other. In principle, I can enhance the dark couplings without spoiling the standard model couplings. This is what I'm trying to say. Um, so we don't have to have everything exactly equal to each other. Although the point is I can do this, but they still be coupled to both the dark and the visible sector. Just a little bit of nice, let's say, little result here is that if I look at my overall bound on the overall volume, so the volume has to be smaller than 25, if I take an isotropic Calabi-Yau, so I look at the volume formula, so I have Kijk, Vi, Vj, Vk, where Kijk is just the triple intersection number, and the V's are the two cycles volumes. Then in the isotropic Calabi-Yau, we know that all the two cycle volumes are the same, and so the bound where the overall volume has to be smaller than 25 leads to a bound on each two cycle volume being smaller than 3. And so since I know the properties of my triple intersection number, since it's a rank 3 antisymmetric tensor, it grows, like the number of entries grows as h1 to the third, then the overall volume of my Calabi-Yau, I can rewrite it like this. Now, if Kijk, this is assuming that all my triple intersection number are of order 1, but they can also be higher. So this is a very, let's say, relaxed. It can be much more restrictive bound. So I get this, let's say, new bound that affects both H11 and V, and I can plot this. So I can plot the overall volume as a function of H11, and I can see, so this here is the overall volume bound, and then I can look what happens for each by taking the volume of the two cycles to be equal to 1, and this tells me that the maximum allowed value of the maximum allowed number of axions in my theory is 9. If I take the two cycle volumes to be of order 2, then automatically I already have that the axions can at most be 5. 3, then they at most can be 3. So this really is a bound on the multiplicity of the axions in my theory, which is very strong because in type 2b, for example, we said that there can be order 100 of axions. Here we're saying that there can be at most 10 if I take v equal to 1. Okay. So now we look at what are the potentials or the masses, let's say, that the axions get. So I have 3 contributions. So everything that couples to the first T8 will get a contribution from the standard model, from the QCD, because we want to solve the strong CP problem. So A plus NIBI will get a contribution from the QCD potential. Then I have Gaugino condensation from the second D8. So everything that couples to the second D8 will get a Gaugino condensation contribution. So A minus the sum over I and IBI. And then I have worksheet instanton contributions on my two cycles, which give me, so the sum over CIBI will get some contribution. So for each, let's say, BI, I get one of these. And the point is that the scale of the worksheet instanton contributions goes like e to the minus 2 cycle volume. And the point is that, again, if I look at my overall volume bound and I take an isotropic Calabi-Yau, I know that the 2 cycle volume has to be smaller than 3. So e to the minus 3 is really not a small number. And therefore, I imagine that in my theory, I will have mostly heavy axions. I can take a limit where I have an anisotropic Calabi-Yau, so for example, a fibered Calabi-Yau, where all of the volume is in one of the two cycles, and then all the rest of the two cycles are very small. And in this case, for example, I can take one of the two cycles to carry 30 units of volume, and therefore I have one fuzzy dark matter axions, and the rest will be extremely heavy. Okay. So, but this brings me naturally to the quality problem. So we said that the QCD potential will give a mass to whatever is coupled to the first T8. So A plus the sum over I and IBI. So this is the combination that will solve the strong CD problem. So this potential will try to drive A plus the sum over I and IBI to minus delta, where minus delta is the quark mass matrix contribution. Um, and then I have Gaussian condensation, so I'll try to drive A minus and IBI to zero. And then I have the Washington instanton contribution, so I have H11 terms that will try to drive some combination of BIs to zero. And so the point is that if I have H11 BIs that are set to a specific number, and then the Gaussian condensation sets A as the sum of an IBI, I have no more the freedom to drive A to minus delta halves. Because I have one extra, one too much, one too many contribution to the potential. So what I can do is that I can either lose one of the Washington instanton contributions by making a two-cycle volume extremely large, and so going to an anisotropic Calabi-Yau, such that the contribution from that Washington instanton is negligible. Or I can go to a case where I brachiate completely and I have no Gaussian condensation. So we look at these two cases. So if I do have Gaussian condensation, but I only have H11 minus 1 contributions of the Washington instanton, then what this means is that I have to have one of the two cycles to be extremely big, at least bigger than 25, such that the overall theta, so the overall theta parameter, which is the sum from the QCD one, and this delta theta, so the shift coming from these worksheet instantons, these have to be smaller than 10 to the minus 10 in order to solve the strong CP problem. So since I know I'm
Sorry,
in an
Margherita, you have a bit less than 5 minutes left.
okay. So since I'm in anisotropic Calabi-Yau, then what happens is that I can rewrite this as just 2 times the overall volume over the triple intersection number. So this becomes a lower bound on the overall volume of the Calabi-Yau. So I can now write theta effective over V, and I can see that already k equal to 1 is excluding most of the parameter space. K equal to 2 is already excluding everything. So I can solve the strong CP problem, but I need to have a triple intersection number which is equal to 1, and the volume which has to be very big, relatively big in the sense. It's much easier to solve this by breaking all of the E8 to U1s and having no Gaussian condensation because I have no condensing gauge group. And in this case, I really have no potential. This term really vanishes. So I can have both isotropic and anisotropic. And in this case, I have no fuzzy dark matter. In this case, I can have a fuzzy dark matter. So these are the examples. So you said I have okay, I can go very quickly in this example and then I go on. So in this example where I only have one axion, this means that I have one model-dependent axion. So I have the universal axion and the model-dependent axion. And so in this case, for example, we'll see that, I think I have it here. Yeah. So if I have no Gaussian condensation, my QCD potential looks like this, and my Washington instanton looks like this. So I go to an orthonormal basis, and here I find that only phi 1 will couple to the first D8, and then I have phi 1 and phi 2 that couple to the second D8. So this is one of the examples where I can really decouple one of the two axions from talking to the standard model. So these examples do exist, they're just a little bit more complicated. And so we will have these Chern-Simons couplings, but let me not go into this. But the point is that if I have no Gaussian condensation contribution, then I will have two axion masses. One will be of the order of QCD scale, and one will be much heavier and will be of the order of the Washington instanton contribution. So here I can solve the strong CP problem. I have no worries. And here I will have some specific Chern-Simons coupling. But if I do have Gaussian condensation, then the point is that the Gaussian condensation scale will be much bigger than the QCD scale and also the Washington instanton one. And therefore, I am not solving the strong CP problem because I'm freezing my fields, let's say, at a scales that are higher than the QCD scale, so I have no freedom left to move around the fields. And so this is the case where I cannot solve the strong CP problem. This is this example with a quintic. So I take H11 equal to 1. I know what the triple intersection number is. I know what the second Chern class is. So I take a specific gauge bundle where V1 and V2 are SU4, and this is a line bundle. This is the monad construction, but I think I'm not going to go into this because it's a bit too long. But anyways, this is the point. I just wanted to show you that you can really see what these look like, and you can find what the Chern-Simons coupling of these things are. This is the example with H11 equals to 2. So again, not going into too much details, but just to show you, if you don't have Gaussian condensation, but you do have isotropic Calabi-Yau, then you can solve the strong CP problem, but you cannot have a fuzzy dark matter. If you don't have an anisotropic Calabi-Yau, then you can solve the strong CP problem and have a fuzzy dark matter. If you do have Gaussian condensation, things are a little bit more tricky. So in the isotropic case, you cannot solve the strong CP problem and you cannot have a fuzzy dark matter. But when you have an anisotropic case, then you're borderline solving the strong CP problem and you cannot have a.
Yeah.
Sorry? Okay. I was. Anyways, this is kind of a recap as well. So let me just finish with the kind of comparison. So in type 2b, we have large cycles which can be tuned. In heterotic, everything is bounded. The masses are log distributed in type 2b. In heterotic, typically, we expect to have heavy axion masses. It's natural in type 2b to have a fuzzy dark matter. It's hard to obtain in heterotic. You really have to kind of struggle for it. The axion couplings often will be to hidden structures in type 2b, whereas in heterotic, we saw that there will be cases where we can disentangle the axions from the coupling to the standard model, but usually they will be universal. So you will have couplings to both the first Y8 and the second Y8. In type 2b, the quality problem is not a problem. In heterotic, so you can solve it, but you kind of need to be specific about it. So the point is just to say that in type 2b, you have much more flexibility. So somehow everything is nicer in a way, but you have much less control. In heterotic, you have much more control. So that's a way in which that's nicer, but you have much less flexibility. So everything is kind of given to you by the theory in 10 dimensions. So let me just conclude here. I don't know if I have time to kind of read out my conclusions. But just wanted to say axions are generic. The theoretic string theory is very nice because it gives you a concrete setup which you cannot really escape from. You can play around with things a little bit, but it's not as free as in the type 2b case. So I think I will conclude here, and thanks a lot. Let me just
Thank you,
do this
Margherita.
so that I can see.
Are there questions for Margherita? I don't see
I
any.
can have
Okay.
a quick one.
Okay, go ahead.
Can I ask
And
a
then
quick one? Yeah.
Yeah, and then we have
Hi,
Mimi.
Maggie.
Yeah, go ahead.
So just a quick question. I had to step out. Maybe you said it. Do your result depend a lot on how I break E8? So if I break it for, I don't know, to SU5 cross SU5, or is there a big difference between that group and if I break it completely to U1 to the 8 or something like this?
Right. So do you mean the say dark E8 or the visible E8? Because that's kind of different. So the thing that
I guess I'll ask for
changes
both then.
mostly, yeah. So the thing that changes mostly, let me see if I can show you, is this here,
So now
right?
we see
So these
black.
are the, oh, how do you, why do
We
you
don't see it
black?
anymore.
Okay, wait. Do you see it now?
Yes.
Yeah, nice. Good.
Yes.
Yeah.
Okay. Okay, so the thing that changes is this Ni. So the coupling of the Chern-Simons coupling between the axion and the gauge field, in the sense that depending on your second Chern class, you really are changing the number,
Okay.
right? That you
But the
get
number
at
will
the
not
end.
change a lot, right? It will be the
I
same
mean, it will
order of
not change.
magnitude.
Yes, but that's very important for phenomenology.
Okay, yeah, fair.
So it does change a lot in that sense. But the story somehow doesn't change too much, except that if you break the dark group, the dark gate to all you ones, because in that case, the important part is this. in the sense that if you here you have all of these contributions, you have no freedom to solve the strong CP problem because you have one too many. So if you don't have Gaugino condensation because you're breaking everything to U1s, then this term goes away and you regain the freedom to actually solve the strong CP problem without doing a lot of complicated things. I don't know if this answers your questions.
Yeah, very good. Thanks a lot.
I think we have a question, Munich. Go ahead.
Can you hear me?
Yes.
Very slightly, but yes.
Okay, great. Thanks for a nice talk. So I'm not really familiar with heterotic model building. Do you have to care, since you have a relatively small volumes, do you have to care about GS or MS corrections?
So you can. So the point is here we're talking about large volumes in the sense with a small L, not a capital L, in the sense that it's not really large volumes, right? You would expect that you don't care about corrections, right? If you go to very, very big volumes. And here instead, this volume bound will tell you that you cannot go to very large volumes. So for sure, there's I mean, all the volume building has always been done in this smallish kind of volume, but largish at the same time. Um, but of course, you should think that there might be some corrections that are important. This is something that in exotic model building is always kind of seen and not really important. Yeah, that's one of the caveats, let's say.
I see. Well, thanks.
Yeah.
Sorry to continue this very quickly, but here you not only you have volume that is, say, order 20, so you could say, okay, in some sense it's large, but on some point you also mentioned cases where you have really, well, cycles of volume actually one. So is that even more dangerous or?
Yeah, so that's why here, where do I have it? Wait, did I lose it? Maybe it was here. Yeah. So that's why here I have this in parentheses. So because requiring to solve the strong CP problem would require all the other axion or the other two cycles to have volume of order one. So you can solve it, but it's really pushing it. So yeah, I completely agree. So when I talk about example, this is where I say, for example, you have volume one, right? The point here is that I just wanted to plot it, but I don't think volume one would be your safe. You need, I think, at least volume two, right? I mean, you need 2 pi times the 2 cycle volume to be bigger than 2 pi. So somehow volume one is, I think, a bit too low.
Okay, thanks.
Okay, very good. So I don't see any other questions for now. If you have some, please wait until the end, and I think Margherita will answer your question. And now we'll move on to the second talk of the day. Thanks again.
Thanks.